This is one of several biggest puzzles in modern natural science. It is really maybe top 5, not just in astrophysics, there's in the whole physics. There is a population of relativistic electrons and positrons in the halo of spiral galaxy like Andromeda galaxy. Then we expect a thing called inverse Compton emission from them. It is when electrons basically hits stellar photons, and through Compton scattering mechanism they upscatter them into the gamma ray band. This is the mechanism of generation of gamma ray emission. This plays a bit important role in the whole astrophysics. And a peculiar thing in this specific setting is that such inverse Compton gamma ray emission would have, it must have, asymmetry between different hemispheres of the spiral galaxy, which we observe from a side, and when it is inclined with respect to our line of sight. This is not the case for our Milky Way, because we sit exactly in the plane, so it is symmetric. But any other galaxies would be asymmetric. And before, nobody outlined this effect, and we were the first who theoretically calculated it numerically, carefully. We confirmed that it actually exists. This kind of asymmetry, it's at the level of 10% or 20% in terms of emission intensity between hemispheres. And in future, it can be detected and measured by future gamma ray telescopes. And the measurement of this asymmetry can help a lot in understanding of the exact emission generation mechanism. We already saw gamma rays from Andromeda, but we don't know yet what mechanisms produce them. It could be, say, usual cosmic ray interactions with gas, it could be millisecond pulsars, or it could be annihilating dark matter, which we aim to discover at some point. This story began almost already 100 years ago, in 1930s, when famous American astronomer Fric Cviki, he was studying galaxy clusters, and he noticed that galaxies in clusters move too fast. They move very fast to be kept together by gravitational field produced just by themselves, by their visible matter. So we see visible matter in galaxies, we can reasonably convert, calculate masses of galaxies, and this mass is very insufficient to provide such a strong gravitational field. And the discrepancy was huge. It was like by 5 times or even 10 times. And this naturally led him to the conclusion that some invisible matter must exist inside the cluster to provide strong enough gravitational potential to serve such high galactic speeds. And this was called dark matter. So some invisible matter. So it doesn't seem to interact with light by anyhow, say absorption of light, emission of light. So it appears only by its gravitational interactions. Around 1970s, this question was considered again, and the same thing was noticed in just nearby galaxies, particularly Andromeda galaxy. This was done by another famous astronomer, Vera Rubin. And same thing was noticed that stars move too fast to be kept by just themselves. So rotational velocity of galaxies, basically this is the speed of rotation of stars and gas around the center. We talk here about a disk galaxy. Finally, we arrived to an understanding that the universe cannot work with just ordinary matter. Modern cosmological precise measurements of cosmic background radiation, CMB, found out that the dark matter in modern universe, by its mass density, is about 5 times more abundant than ordinary matter. Practically, from experimental point of view, I mean observational point of view, it's a bit difficult because we need to measure the emission intensity very precisely. But this is very difficult in gamma ray band, contrary, say, to radio band. In gamma ray band, we have very limited statistics of photons. So, I mean, overall number of detected photons is very small, hence statistical uncertainty for flux is large, and we need a huge effective area of instrument to measure precisely. So in practice it is kind of difficult, but we still can be elaborating this opportunity in the context of future very sensitive instruments like AMS 100, Cherenkov telescope array, and etc. This is considered historically to be the most probable and motivated and the best candidate. So these are elementary particles which have not been discovered yet. They are purely theoretical and hypothetical. The whole story of dark matter assumes that it is composed by something non-baryonic. So it cannot be something made of ordinary matter we get used to, like black holes, brown dwarfs. So just cosmological considerations related to the early universe and structure formation require dark matter to be something else, and most likely this is composed of some yet unknown elementary particles. And this candidate, briefly called WIMPs, came quite naturally from both cosmological considerations and the particle physics considerations. These are kind of different worlds in physics, but they are deeply interrelated. Weakly interacting particle mean that this particle interacts through weak fundamental force, like neutrinos do it, etc. And likely such any dark matter particles initially were produced thermally in the early universe. This means that early universe was very hot, very dense at the beginning. A lot of different particles were mixing together, transforming to each other, annihilating. So this is called a thermal bath. This is like a full equilibrium, everything is symmetric, it's very hot. And once universe was expanding and cooling down, some species freezing out, such a term, meaning they were going out of equilibrium and getting frozen for the rest of time. And this is a way of production. WIMPs, in this sense, are assumed to be supersymmetric partners of usual standard model particles which we know. It was a very big hope to discover these particles at Large Hadronic Collider, LHC. This was a big hope, but unfortunately it did not work out. Dark matter is not necessarily WIMPs. There are a bunch of candidates, very many candidates. It could be, say, as well, axions. This is another hypothetical particle which was theoretically predicted back to 1970s and 80s. Again, it is a natural candidate from astrophysical point of view and from particle physics point of view, because standard model needs an axion to resolve very basic field theory questions in quantum chromodynamics. Dark matter must be literally matter. Yeah, but at the same time, the Notagot knew that here success is not guaranteed, because it must not a priori manifest itself by any other way than gravity. I can communicate and collaborate with anybody in the world. It would be actually much easier, because when I do it in Russia, it's there is a prejudice nowadays, and various different scientists, it depends, they may refuse to communicate. That's why here it should be better. One thing which I like a lot is a high degree of academic scientific freedom here. It is very liberal in the sense that I am allowed to work on basically whatever I want, and I am not restricted by short-term contract. So, I mean, this kind of policy creates a very right environment for science, because in Western countries typically it's a lot of restrictions, short-term positions which do not allow researchers to realize and plan long-term projects. It's very kind of frustrating for life, and usually scientists like foreigners, they are employed to work for somebody else's project. And but for motivated scientists, it is important to have freedom to choose what to do, and to have an environment for real science in the form of real exploration of nature.